tonight is by Dr. Steve Barrett, who is a Senior Research Fellow at the Department of Physics at Liverpool University. He has many research interests, including all aspects of imaging, image processing, and image analysis. This includes medical imaging and microscopy at all levels, from atoms and molecules up to Earth materials, and also astrophotography. He does outreach talks to schools and astro societies and U3A groups, etc. And one of his outside interests, in common with our vice chairman, is going on safaris, apparently. So welcome, Dr. Barrett, and over to you. Lindy, if you'd like to mute everyone.
Mute everyone, yes, yeah. I shall mute everyone now.
And can I also suggest that because we have quite a large number here, can I suggest that people turn their cameras off to save a little bit of bandwidth? Otherwise, Zoom sometimes struggles.
Okay.
Okay. Okay, let me just get my camera in the right position.
Yes, you're in now.
Okay.
I'll mute myself as well now.
Okay. Good evening, everybody, and thank you for this invitation to talk to you about 200 at 70, the 70th birthday of the 200-inch telescope at Palomar. Let me just remind myself to switch over to PowerPoint. For me, the Hale telescope started with this image. It was taken in 1951, but I think I must have seen this image somewhere in the early 1970s when I was at school and I looked up an atlas of the heavens and I saw this image printed there. And it said underneath, taken by the 200-inch telescope at Palomar. I looked at that and I thought, what is it? How was it made? What's it made of? And this, more than any other image, got me hooked on astronomy when I was a young, whatever it was, a young teenager back in the 70s. But of course, the story of the Hale telescope doesn't start in 1951. It starts much earlier. So I'm going to say a little bit about George Ellery Hale, the billionaire who managed to get funding for the largest telescopes in the world, the 40-inch, followed by the 60, followed by the 100-inch hooker, followed by the 200-inch. And when it comes to building the 200-inch telescope, I'll be looking at how a site was selected, how the mirror was made, and how the telescope was put together. And then I'll have a little look about what it's doing now, and then I'll finish with some acknowledgements of where I found most of the material that I'm presenting this evening. So George Hale had a rather remarkable life. He was a well-respected solar astronomer, astrophysicist, but he's remembered best for the fact that he had the vision and the drive to build the largest telescopes in the world. That started with the 40-inch refractor that was operational in 1900 in the Yerkes Observatory, 40-inch diameter lens. And then later we came to the era of reflecting telescopes. And when Hale became the director of the Mount Wilson Observatory, he oversaw the building of the 60-inch reflector and then the 100-inch hooker reflector finished in 1918. So the idea of building the world's largest telescope for any of us would be an amazing thing. But Hale did it not once, not twice, not 3 times, but even after 3 times, he still wanted to go further. Notice that the diameter of the lens or mirror in each of these cases goes from 40 to 60 to 100, in each case going up by half as much again. So the effective collecting area of the objective or the mirror going up by a factor of 2. But when it came to thinking of what do I do next, Hale wasn't satisfied with the idea of going from 100-inch to 150-inch and doubling the area of the mirror. He figured out the best thing to do was to really leapfrog the next telescope and go all the way to a 200-inch diameter, 4 times the area. So barely had the Hooker telescope been finished and operational in 1918 when Hale thought, how do we get a larger telescope? It took quite a few years to get the funding, but in 1928 he approached the Rockefeller Foundation and persuaded them to pledge $6 million to build not only the 200-inch telescope, not only the telescope and mount and observatory dome, but the entire infrastructure of the observatory. $6 million in today's money, that would be a fraction of $1 billion. That's no mean feat for one person to persuade a foundation to part with that amount of money. Having got the funding, where do you decide to site this particular telescope? Modern telescopes, you might think about going to the middle of the Pacific and putting it on the islands of Hawaii, or maybe the Canary Islands in the Atlantic, or perhaps in the high mountains of the Andes in Chile. But Hale had reasons for wanting to stay local. As far as he was concerned, the center of the universe was Los Angeles. That's where it was claimed were most of the world's great astronomers. So there's the island of, there's Los Angeles, the island of Catalina a little way to the south. Mount Wilson Observatory is indicated there, and you can see that Los Angeles is dangerously close to Mount Wilson. At the time Mount Wilson was put together and ultimately the 100-inch was constructed, that was a reasonable place to do observing. But Los Angeles grew, and then you had San Bernardino and then San Fernando, and it started to envelop Mount Wilson. So Hale thought it's a good idea to keep the telescope close because the astronomers are centered around Los Angeles, a somewhat parochial view, but okay, we'll let that go for the moment. But it is true that a lot of the mechanical workshops and the optical workshops were based in Los Angeles. And therefore it made sense to Hale to keep the observatory close rather than position the observatory halfway around the world. So given that Mount Wilson is now being surrounded by the light pollution of Los Angeles, San Fernando and San Bernardino, he looked elsewhere. He sent out scouting parties to various sites in California, to high mountain tops, to get them to check out the seeing conditions. And eventually he produced a list of a short list of a half a dozen mountains within California that all had excellent seeing conditions. Before making the selection, he thought he'd better just perhaps check with the geologists. So he went to the geology department in Caltech. That was headed by a certain Professor Richter, yes, that Richter of the Richter scale, and asked the geologists, of these 6 places that I've chosen, is there any particular reason to choose one over the others? They said, well, maybe you want to rule out this one and that one because they're sitting on the San Andreas Fault. Not a good idea if you want a nice, stable telescope. But one of the sites you've got on your shortlist is this one, Palomar Mountain, a little way to the southeast of Los Angeles. It was pointed out by the geologists that Palomar Mountain is essentially a slab of granite, 30 miles long, 10 miles wide, and 25 miles deep. So it's quite a few trillion tons of solid granite. And it was basically stated that even if California is hit by an earthquake, that is not going to move. So if you bolt your telescope mount onto that mountain, that's the stablest thing that you could possibly hope for. So that's why the decision was finally made to go with Palomar Mountain. It's far enough away from Los Angeles not to be too much of a problem. There is a little settlement south of Palomar called San Diego. It has, of course, grown into a rather big city in the meantime, and it is producing some light pollution on Palomar's southern horizon, but it is something like 60 miles away, so it's not considered too bad. And Palomar is still considered a site of good seeing. So what does Palomar look like? It's a rather beautiful environment. It was essentially not a national park, but it was parkland before the observatory was sited there. That's what it looks like in the autumn. I visited it some years ago. What's that? Oh, almost 40 years now. When I was a student, I went visiting and saw the telescope and saw the observatory. I was rather struck by how amazing it was. At the time I said, one day I will have a house with a garden big enough for an observatory that looks like that. Okay, that hasn't quite come to pass, still an aspiration. But when I visited there in shirt sleeves back in the May of 1982, it was difficult to realize that because of its altitude, it does actually get quite cold there from time to time. At 6,000 feet or 1,700 meters, it does get rather heavy snowfall, so you do have to worry about making sure people can shovel the snow off the top of the dome. It's 6,000 feet thereabouts, but in order to get anything up to the observatory site, which is up here somewhere on the right, everything has to go up a rather windy road called the South Grade, and that is something like 12 miles of hairpin bends backwards and forwards. So everything had to be taken up, not just the nuts and bolts of the telescope and the mirror itself, but all of the steel work for the mounting, all of the steel work for the observatory, the entire observatory site effectively had to be taken up piece by piece over a period of many years. So the funding had been established in 1928, and now it was established where the observatory would be. So what's the next decision that has to be made? The basic one is, what form is the telescope going to take, and what sort of mounting are you going to be using? So amateur astronomers know that there are a number of ways that you could in principle mount a telescope. The German mounting with a counterweight, or the fork mounting, which doesn't need a counterweight, but you still have a relatively large mass trying to pull the mount over. Or the most stable way of doing it is the so-called English, or sometimes called the yoke mounting, which is a bit like having two forks back to back. So the yoke mounting is supported from the north and the south bearing, and thus you have a very stable system. It's interesting to note that when Hale was thinking about the three previous telescopes, each of these was used, in the sense that when the 40-inch was designed, the 40-inch Yerkes refractor, that used the German mount with a counterweight. When it came to the 60-inch reflector, that used a fork mount. Perhaps it doesn't look too much like a fork because the arms are rather short and stubby, but it is a fork mount. The center of mass is quite low for this particular structure. And when it came to the Hooker telescope, the 100-inch, there they adopted the English mount to get the maximum stability. Having a north and a south bearing meant that the Hooker telescope was a very stable structure. But of course, on going from 40 to 60 to 100, we are increasing the size of the aperture by approximately 50%. And so we're roughly doubling the area. But the next jump is going to 200-inch, which is quadrupling the size, the area of the mirror, and potentially taking the mass up by a factor of 8. So how are you going to decide what sort of mounting you want? Well, there were a couple of factors, but the main one that Hale thought about was the fact that he did not want the 200-inch telescope to suffer from the same limitations as the 100-inch Hooker. With respect to the English, or the yoke mount, meant that no observations could be made within 30 degrees of the North Celestial Pole. You can see from the picture there that if the tube starts to point towards the north, it would eventually foul the yoke mounting. So everything within 30 degrees of the pole is out of bounds. So an entire disk of sky, 60 degrees across, was a no-go area as far as the Hooker was concerned. And Hale did not want to suffer from that same limitation. He liked the stability of the yoke mount, but he didn't want to suffer from that limitation. The other problem that was perceived in the Hooker that Hale didn't want to reproduce was the fact that the mirror was made of plate glass, which expanded and contracted quite a substantial amount as the temperature changed, which distorted the mirror surface. So during the day, you try and keep the observatory at the same temperature as the forecast for the night. But of course, the forecast for the night temperature could be wrong by a couple of degrees, and you would have to let the mirror adjust to the nighttime temperature, and that adjustment could take hours, and during those hours the shape of the mirror would be wrong because of the expansion or contraction of the glass. And again, Hale didn't want the new 200-inch telescope to suffer from the same limitations. So firstly, what about the mount? It was decided that yes, a yoke mount is a good idea, but we want to be able to see to the pole, and so it was decided that the best solution is to have an iconic horseshoe yoke mount. So the telescope tube is mounted in between the two arms of the yoke, but the yoke has a simple mounting at the south end, but at the north end, the yoke changes into a very large horseshoe, as you can see here. That means that if you wish, the telescope tube can be moved and pointed directly to the North Pole by simply having the tube nestle inside the horseshoe itself. And it means that you have one bearing in the south, and then you have this very large bearing surface, which is the outside of the horseshoe itself, which sits on pads in this northern pier to give us the smooth motion of the telescope. So that's how we get stability, and we don't have any limitation in the sense that you can now move the telescope to see any part of the sky. What about the second aspect of the problem? The 100-inch mirror. This is a picture looking into the side of the 100-inch mirror. So at the very top there, you can see the silvered surface, and we're looking into the green glass itself. And you can see the glass is stratified. It looks like it's been poured at different times, and part of the glass has partially solidified when the next molten glass was poured in, and we end up with these strata. Not only that, you can see there's a lot of ripples in there, and there's a huge number of air bubbles. So in the question, can the 100-inch mirror be scaled up to make a 200-inch mirror? Basically, no. Using the plate glass would result in the same distortions with changing temperature, and they would be so much worse because the mass of the mirror would be some 8 times larger, and so the effect of the distortions would be so much more dramatic, and it would take a very long time for the mirror to come into equilibrium with the nighttime air. So Hale decided not to use plate glass, but to move to low expansion glass. So he went to Corning Glass Works and figured out a way of making a large mirror using low expansion glass. To avoid having a mirror that was 8 times heavier, twice the diameter, 4 times the area, if it was twice as thick, it would be nominally 8 times heavier. They had to figure out a way of saving weight so that we didn't have a huge mirror that was so heavy you could barely lift it and point it in the right direction. So let's have a think about how mirrors are made. If you have a mold, circular, seen from the side, and you pour in glass, the glass fills up to the edge of the mold, and you end up with a pancake. Here the pancake is just seen from the side. So it's a pancake, roughly speaking, flat on the top and the bottom. Once you've filled the mold up with glass, you then allow it to solidify by letting it cool to room temperature. Once it's cooled to room temperature, you can grind that top surface down to the relevant shape and then coat it with a thin film of metal so that you have the maximum reflectivity. But part of the problem is how you cool it down to room temperature. If you've got a very large, massive piece of glass and you simply cool it down too quickly, what will happen is the heat will be lost from the surface of the glass, but it will stay warm in the central bulk glass material. So you'll end up with different temperatures in different regions of the glass, and that will mean the glass will contract at different rates because of the different cooling at the surface compared to the cooling in the middle, and that will introduce stresses in the glass, and that again will ruin its effect. It will ruin the way that it reacts to changes in temperature in the future. If you simply take the 100-inch mirror and scale it up to 200 inches, it was calculated that the length of time over which you would have to allow it to cool to allow it to anneal and not introduce any stresses in the glass, the length of time to cool from the melt to room temperature would be approximately 10 years. And nobody figured that that was a good idea to have a 10-year program to allow the glass to cool to room temperature. So they needed a faster way of doing it. One way is to replace the glass with low expansion glass so you can cool it a little more quickly. The other method is to reduce the mass of the mirror. So they decided to fill the mold with cores, so-called cores, which are fire bricks around which the glass will flow when the glass is poured into the mold. So that means that, again, you have to allow it to cool to room temperature, but because there's less glass there, you can do that a little more quickly, perhaps in as little as 1 year rather than 10 years. You cool down and then remove the cores, which leaves air in the back there, and it leaves ribs of glass in the back. So you end up with a structure which is very stiff and very strong. and then you simply grind the top surface just as you would before and coat it with metal. So the result is a mirror with the front surface that's exactly the same as we saw just a moment ago, but now it's got a ribbed back and a substantial amount of glass is no longer there. So you end up with a very stiff and relatively light structure. And that's what was needed for the 200-inch mirror. In this particular drawing, we see a cutaway of the mirror. So there's the mirror surface there, and you can see these voids where the fire bricks were and then removed. Some of these voids are simply left full of air. Some of these voids are actually full of the mirror support mechanisms. You can see some of these things that look like pistons that are in place supporting the mirror. These mirror support systems were extremely important to make sure that when you've got a mirror as massive as this and you want to point it to different parts of the sky, where of course gravity would then be pulling in different directions, it's very important that you support the mirror to make sure that the mirror surface does not distort. So we've got this idea of putting in fire bricks into the mold before you pour the glass in order to save mass. But one of the people at Corning said, well, we could use fire bricks. That's a perfectly sensible way of doing it. But why use fire bricks? Because we are Corning. As well as making scientific research instruments like this mirror, we also make thousands upon thousands of custard jugs. That's where the Pyrex name comes from. So why don't we just fill the mold with Pyrex jugs and then pour the glass around those? Why use fire bricks? I believe this was taken seriously until they did a test and realized that it didn't actually work, because they couldn't then remove the, couldn't easily remove the jugs once the glass had been poured around them. They were effectively bonded into the structure of the mirror. But it's a nice thought that perhaps the world's largest telescope could have been made with a whole load of Pyrex jugs sitting in the main mirror. Didn't actually ever happen. Shame. So that's what the mold actually looked like, 5 meters in diameter, and you can see these fire bricks with slightly rounded edges have been placed throughout the mold, such that when the glass runs between the various fire bricks, it effectively makes a large pattern of ribs, which gives it the strength. There's a large plug there in the middle in order to produce a hole in the main mirror, because we want to eventually use it at the Cassegrain focus, which we'll see in due course here. So that's what the mold looked like. I appreciate that you can't see all the detail of this. This is just to give an overview of the Corning glass works in 1934, where on the right, there's a very large tank containing the molten glass, and then teams of individuals with large ladles, looking for all the world like big ice cream scoops, would scoop glass out of the tank and then take them to the mold, the oven that contains the mold, and then pour the glass into the mold. And we can see that in action in the following videos. So here we have some individuals putting the ladle into the tank, and then everybody jumps on the left-hand end in order to pull the ladle out of the tank. Water is sprayed on the ladles to make sure the ladles don't melt, because we're talking about very high temperatures here. And from a slightly different angle, we can see the ladle going into the tank, being dipped into the molten glass, and then again, everybody jumps on the end, and out it comes with about 100 kilograms of molten glass. Excess glass is scraped away, and a little more water is played upon the ladle to make sure the ladle doesn't get too hot. And then the water is taken away and the ladle gets taken to the oven with the mold inside, and then the ladle is turned over to pour the molten glass into the mold. Any excess glass that's still in the ladle when it's taken out is then poured into a wheelbarrow, and somebody takes that wheelbarrow back to the tank where it's recycled. And this process would then continue and be repeated hundreds of times throughout many hours of a day to get 20 tons of molten glass into the mold. So there's a static picture giving you an idea of what it looked like. The weight of the ladle was taken on this mechanism. So there's these tracks that allow the ladle to move from one tank to the mold. And it's controlled by the various glass workers, and the guy at the front, who's got a visor, which is gritted in his teeth, he's in charge of deciding where the ladle gets poured into the mold to try and make a nice even flow of glass around the various fire bricks within the mold. There's always a supervisor there with a hat as well on the left-hand side, making sure that everything works according to plan. The casting in 1934 went pretty much to plan, but unfortunately they had problems during the next year when they were cooling the mirror down from the melt to room temperature. Some of those fire bricks that were supposed to be fixed to the bottom of the mold, some of them unfortunately popped loose. And fire bricks are lighter than glass, and so they simply floated to the surface. In addition, some of the bricks, you can see some of the bricks on the outside of this particular oven. There were similar bricks on the inside of the oven, and unfortunately, over time, some of them became loose and fell onto the surface of the mirror. So by the time it eventually got down to room temperature, they took the bricks out, and of course, they left then large gouges in the glass. It was thought perhaps they might be able to save this because remember, they're going to be removing large amounts of glass to grind it down to the correct shape. They're going to be removing many, many tons of glass just to get the figure right. But unfortunately, the gouges towards the edge of the mirror were just a little bit too deep, and this was considered unusable. So this was consigned to the Corning Museum, and they had a second crack at it the following year in 1934. Learning from their mistakes, they made sure that the fire bricks were bolted down to the bottom of the mold so they wouldn't pop up, and they made sure the inside of the oven had no loose bricks that could possibly fall onto the surface of the mirror. The second casting in 1934 was successful, and the first mirror blank, which was ruined by these various effects, we didn't have the same problem. The second casting was essentially perfect. Here, an individual is shining light through one of the ribs to make sure there's no sign of any stresses in the glass that indicates there was any problem with the casting or any problem with the very long cool down, which took the best part of a year. Here's a publicity photo, just reminding you that the aperture in the middle is about 1 meter or so in diameter. There's no particular reason why this gentleman is measuring it. If it's wrong, it's a bit late now. So this is just to remind people just how large the mirror is by showing a human in the middle Cassegrain aperture. And Corning were quite keen to use this in their advertising. The eye that sees 6,000 million miles. Why that particular number? Well, it was calculated that the 200-inch telescope ought to be able to see galaxies that are 1 billion light years away. So they simply took 1 billion light years, calculated it in miles, and that's the number you end up with. Notice that when dealing with the public, for some reason, very rarely did you refer to lenses and mirrors. It was nearly always the eye, the giant eye at Palomar. For some reason, they thought that was more palatable to the public. So the second mirror wasn't exactly trouble-free in the sense that during the 1-year cool down, they did have problems. They weren't insurmountable, but for instance, they had a local river just next door to the Corning glassworks. The mirror flooded and the water came into the glassworks, and it basically was threatening to hit the transformers, which were supplying electrical power to the annealing ovens to keep everything warm and gradually cool down. So they had a real problem when they realized that, well, if the water hits the transformers, that's really bad news. So what do we do about that? They also had a minor earthquake, but again, that didn't cause too much of a problem. So they were very relieved when at the end of that period, they could announce that the glass mirror that they had produced was essentially perfect in the sense of defect-free. And then they could send the mirror over to Caltech, to the optical laboratories in California, to be ground and polished. You get an idea of the thickness of the mirror there. I wouldn't really want to hold it on one strap myself, but there we go. You can see that the mirror is translucent, some light behind is coming through, and again you can see very clearly the ribbed structure produced by these various fire bricks that were put into the mold in the first place. In terms of the grinding of the mirror, well, the team was 21 men, and it took them 11 years. That's an awful lot of effort for one piece of glass, but you can appreciate, being the largest mirror of its kind by far, they didn't want to get this wrong. And Hale's argument was, you can do it fast or you can do it right. What we're going to do is we're going to do it right. So he wasn't in any rush to get this done. He wanted it to be the best mirror ever produced. So the grinding machine looked like this, a large horizontal turntable on which the mirror was slowly rotated, and then a grinding or polishing wheel would move backwards and forwards on this gantry, and the gantry would move backwards and forwards, and the polishing wheel would rotate. And if necessary, grinding medium was applied to produce the grinding of the surface of the glass. Of course, as they were grinding the material away, they wanted to keep checking that they were grinding it correctly. They wanted to make sure that they were figuring it to the right shape. And so every once in a while, they would stop that process, just wash the mirror down, and then move the mirror to a vertical position for testing. So you can see immediately the absolute need for making sure that your mirror supports were essentially perfect. If you weren't absolutely sure that by supporting the mirror at the back, you were holding it in precisely the right figure, how do you know that what you're grinding when it's horizontal is exactly the same as what you're testing when it's vertical? So that's why they put a lot of thought into how they were going to make sure the mirror support system supported the mirror with essentially no stresses that would possibly distort the mirror surface. So whenever it was in the vertical position like this, they would use a knife edge test from the other end of the laboratory to see what the figure of the mirror was. So here we see the figuring being tested with a knife edge test, and we can see this gentleman there actually doing the test. And that was the best way of making sure that they were producing the figure of the mirror exactly as intended. There's a limit to how much you can test in the laboratory. Ultimately, the only real test of a mirror is to point it at a star and make sure that star comes to the correct focus. So you can do tests in the laboratory, and they took this as far as they could, but the final polishing had to wait until, as we will see in a short while, had to wait until the mirror was actually placed in the telescope. So whilst the mirror was being worked on, the construction of the observatory began in 1936. So they produced piles into the granite, so relatively straightforward because the mountain is just one large slab of granite. So all you need to do is to put some piles down and you have a very solid foundation. It didn't take too long before the walls of the observatory started to grow to the point where they were then at the level at which they wanted to mount the railway track that was going to support the rotating dome. When it came to grinding the double railway track, Hale was asked, well, how smooth do you want these rails to be? And Hale said something like, well, you know, the nearest thousandth of an inch is probably good enough, which for an observatory that size is quite a remarkable feat. The bottom line is that Hale and all the astronomers at the time said, what we want is an observatory built in such a way that when the dome rotates, no vibration whatsoever is transmitted to the telescope. The dome weighs about 1,000 tons. So you want to be able to move 1,000 tons perfectly smoothly with no vibrations, no bumps in those rails that would possibly transmit into the ground and hence into the telescope. Once those rails were complete, the actual construction of the dome could start. So there's 1937. And by the time the dome is forming a hemisphere, it's actually now starting to really look like an observatory. Let me use these particular drawings of Russell Porter to give you an idea of where we are. This particular cutaway drawings and some other cutaway drawings that I'll show you shortly were all made by the technical graphics artist Russell Porter. Some of the detail in these drawings might not come across on your screen, depending on the size of the screen you're looking on at the moment. So I'm going to make these drawings available as PDFs afterwards. I'll send a link to Peter so that you can actually look in detail at some of these drawings because they really are quite exquisite. So some of these drawings I'm going to use just as a sort of a guide to where we are in the observatory. So this is a cutaway of the entire observatory. If we just focus a little bit more on the telescope itself, we have a sort of We have a cutaway of the tube in the middle there, of course, and a ghost here on the right showing you where the tube would be positioned if it was pointing at the North Celestial Pole, lying inside the horseshoe. And there's a ghost of the telescope tube to the left showing you where it would be positioned if an astronomer used this escalator to climb in to what we're about to see, the prime focus cage in the middle of the telescope there. So let's just grey that out a little bit so we can see a little bit more detail. That's where the mirror is positioned. So if we're looking at a star which is essentially overhead, the light would be coming down, hit the primary mirror, and then come to a prime focus there in the so-called prime focus cage. This is a cage which is large enough to take an observer, as you can see from this little blow up, this little crop of the drawing here on the left-hand side. This is the first telescope that's large enough that you can place an observer inside the telescope without sacrificing anything other than the central blockage, which you would have anyway if you had a secondary mirror, for instance. Previous telescopes were too small to make that viable. Later telescopes tended to use instrumentation, and there was no need to have an astronomer in the telescope. So this prime focus cage is not unique, but it is iconic to the Hale telescope. So here the observer would sit if they wanted to take prime focus from the prime mirror. The light would come to a focus where the observer could see what they were looking at and presumably have a photographic plate there to actually record what it is that they were trying to study. But if prime focus wasn't required, prime focus, of course, is the shortest focal length you can have, so the widest angle views if you were looking at an extended object, a very large nebula or star cluster perhaps. But if you wanted to look at more detail from a smaller object, you would want a longer focal length. So one of the options would be below the observer in the bottom half of the prime focus cage would be a series of mirrors that would fold down into place to produce a secondary mirror for a different optical configuration. So a second version would be a Cassegrain focus, whereby a mirror would be positioned there at the secondary focus, and then the light would hit the primary, then the secondary, and then come to a focus behind the primary mirror. Of course, this is why we have a hole. I haven't shown it here, but that's why there would be a hole in the primary mirror to allow the light to come to the focus at the Cassegrain focus. The advantage of the Cassegrain focus is a longer focal length, quite substantially longer than the prime focus, not simply double as you might think, but because the secondary mirror is curved, it gives you a much longer focal length, much more detail for smaller objects. The other advantage is you can put a lot of equipment at the Cassegrain focus. There's room behind the main mirror that you can pack quite a lot of equipment in place. And because the telescope itself, the telescope and the mount are so well built, you can actually put a substantial amount of instrumentation at the Cassegrain focus without worrying too much about the balance of the telescope. It's estimated that up to 1 ton of instrumentation could be placed in the Cassegrain focus and the instrument would still be perfectly operational. One third possibility is to get the focal length even longer, and especially if you want to use instrumentation which is too bulky to fit at the Cassegrain focus. Another option is to place a third mirror here at the intersection between the declination axis and the polar axis, or the right ascension axis. By placing a mirror there, now the light from that distant star will hit the primary mirror, then the secondary, then the third mirror, and be deflected down inside the polar axis itself, which is hollow, to allow that light to come to a focus as indicated here. It's called the Coude focus simply because this third mirror introduces this dog leg, or if you like, elbow, and Coude is just French for elbow. So it's an elbow focus, if you like. And the real advantage of this focus here is that it does not move regardless of where the telescope is pointing at the sky. So if you wanted bulky or very heavy instrumentation, you could position that in a static room and know that it would not have to move regardless of where the telescope pointed in the sky. And here you can see an observer in the line of the light coming down through the polar axis, checking that the light is coming through in the right direction. And again, we'll see a video of that later. So here's some of the construction taking place. Steelwork. This is the steelwork that sits directly underneath the north and south bearings themselves. It gives, again, a rough idea of scale. And here you can see the telescope tube manufacture starting. It was made by Westinghouse Construction, and this particular picture gives you an idea of A, how many people were involved in the construction, and also it gives you an idea of the size. This is the base ring of the telescope, which ultimately would support the mirror cell itself. Here's a few items being made. Part of the horseshoe in the top left, that's one of the horns of the horseshoe. In the right and below, you can see various parts of the tube being put together, including what I think is the declination bearing in the bottom right-hand corner there. It was said at the time that putting the Hale telescope together is a bit like building a battleship, except that it needed the precision of a Swiss watch. That was the marriage that was required from the Westinghouse team. When they had most of the items they needed, everything was constructed in their factory before being dismantled and then sent across to California and reconstructed in the observatory itself. So here in 1937, they had essentially finished the telescope tube, and they had this, as it were, dedication ceremony for the tube itself. In the VIP gallery is a certain Professor Einstein there, who was brought along because he was very interested in this particular telescope. Einstein was a theorist. He was only interested in theory, but it was thought that once the Hale telescope was finished, it would ultimately be able to see much further than the Hooker telescope and be able to see either fainter galaxies or more distant galaxies, and would perhaps be able to verify some of the theories of gravitation that Einstein had been developing in the past years. This is a very interesting way of looking at one of the horns of the horseshoe. You can see the structure inside the horseshoe, lots of ribs to make sure it was absolutely rigid, to make sure it didn't flex as it moved backwards and forwards. But also you can see just how thick the metal is on the outside curve and on the inside curve of the horseshoe itself. Roughly 4.5 inches thick plates. And these were bent to shape in a 12,000-ton forge press. Yeah, that's not a misprint. 12,000 tons were used to press these into the correct shape. And again, you can see the thickness of the metal on the outside there compared to the people that are probably in another publicity shot measuring something which is a little bit difficult to fix now if it turns out to be the wrong distance. So that was one particular part of the horseshoe. There's 3 parts of the horseshoe. It was too big to make in one piece, so it was made in 3 pieces and bolted together before they then milled precisely this outside surface. This, remember, is the bearing surface. This is what it's going to be resting on. And so if you want to be able to point the telescope to arc-second accuracy, you need that outer surface to be as precise as possible. So the 3 parts of the horseshoe were bolted together, and then on probably the world's largest milling machine, this outer surface was ground to precisely the right shape. Once that was done, again, the 3 pieces were unbolted, shipped over to California to be reconstructed in the observatory. The south yoke, unlike the horseshoe at the far end, is rather smaller, and it looks a little bit more like a telephone handset when you look at it like that. The actual bearing axis, the south bearing, is in the middle there, and the circle you can see in the distance and the circle in the foreground are where the 2 arms of the yoke would eventually attach to make the yoke itself. And there you can see the south part of the yoke in the distance and the 2 arms of the yoke coming out from that. It's fairly obvious that these 2 elements of the yoke arms are hollow. You can see the gentleman standing there. I hadn't appreciated they were quite so big. I assumed that anybody that tried to get inside would end up hunched up, but you can see from the scale there that they are large enough that you can walk comfortably through these arms. And it only twigged a little while after I started picking these photographs up from the various archive sites that of course it has to be that way because the declination motor is sitting inside one of those 2 arms. So of course you need access to it so that you can go and check that everything is okay. As I said before, everything needs to be taken up the south grade. Remember the south grade, the windy road of 12 miles to get everything up the hill to the observatory height of 6,000 feet. And here you can see one particular piece. I think that's part of the horseshoe going up. 3 trucks were used, 2 to pull it and 1 to push it. Note the name of the company that was chosen to actually get these things up the south grade. I'm sure it wasn't the easiest thing to do, but as far as I know, they managed it without any serious accidents. And every piece of metal for the telescope, for the mount, for the observatory, for the entire infrastructure came up in that sort of way. Everything had to come through the floor of the observatory. In the background there, you can see the trolleys that are holding the dome sitting on the track that was made that we saw earlier. And through the floor of the observatory comes all of the individual pieces that were made in Westinghouse and ultimately the mirror as well. So here we see the south yoke coming through the floor. The south yoke is now parked and part of the horseshoe is coming through. We can already see some of the tube has arrived from Westinghouse, and everything had to be brought in that way. And then, of course, you have a large Meccano set to rebuild everything in its final position. So here in 1939, we're starting to put the tube together. Most of the horseshoe appears to be complete there, the south and the north mountings, and the tube itself is being constructed. We can see this individual there, again, gives nicely the scale. No particular need to deal with health and safety as far as I can see. So people clambered all over this without any harnesses and without any hard hats. Okay, this gentleman is wearing a hat, might not be a hard hat, but he is wearing one at least. And here he's looking at various aspects of the prime focus cage. Where he is now is where the mirrors would be that fold down for the Cassegrain focus. At the top is where the astronomer would sit if they wanted to take prime focus images. At some point, they needed to make sure that everything worked as it should. And so here the tube is simply being moved to point as far south as it can go. It's unlikely that it ever pointed at the southern horizon, simply because that's where San Diego is and there would be a little bit of murk over there. But they wanted to make sure that it is at least physically possible and that all of the gearing works to actually point it as low as possible. So we have a couple of engineers. I assume they're engineers because they got the sleeves rolled up, just checking that everything is working the way it should. And when it comes to moving the telescope, the mount and the tube weigh something like 500 tons, and it was required, or at least an aspiration, that in terms of moving the telescope to point at a particular part of the sky, it was required by Hale that he really wanted to have arc-second accuracy for, if you like, go-to pointing, and sub-arc-second accuracy when it comes to tracking and following an object. And that meant very high precision on the declination and the right ascension drive systems. So this is the right ascension gear wheel. It weighed more than 10 tons. And of course, it meant that not only that wheel had to be made very accurately, but the teeth had to be positioned and ground exceptionally accurate to make sure that the position that you thought you were at was indeed the position you were actually at. So when it came to manufacturing the gear wheels, they spent not quite as long as the mirror, but it took years to grind the teeth on the gear wheels because of the precision required. They needed to grind the teeth and then ultimately polish the teeth to accuracies, again, certainly no worse than of order 1/1000th of an inch, to make sure that the pointing accuracy of the telescope was not compromised. Here they're being ground and here they're being polished into the right final form factor. How do you know when you've got the polishing right? Well, the best way of testing whether it's as smooth as it ought to be is to get somebody with a pipe to run their finger over the gear and make sure everything is absolutely as smooth as it can possibly be. And the final proof is in the pudding. When you get a worm wheel up against the worm gear, then you should have hopefully no backlash and accuracy on the final positioning of the telescope of order arc seconds. How big a motor do you need to move 500 tons? Well, of course, it has to be absolutely huge. If you want to move 500 tons, you need something this size, and you can't tell the size until somebody brings in the oil can. And you can see that the motor is actually tiny. It's, I think, 1/4 of a horsepower. A slightly larger motor was used for slewing, but in terms of just driving it to make sure that it is following at a sidereal rate, 1/4 of a horsepower was all that was required. Even if you wanted to slew quickly from one part of the sky to another, you only needed something of order a few horsepower in order to move it. The gearing and the mounting, especially the horseshoe itself, which was floating on oil pads, the friction was so low that essentially, if the drive system was decoupled, even though it was 500 tons, it was possible to move the entire arrangement just by one person leaning on it, simply because the friction was so low. Had they used roller bearings rather than floated it on oil, the friction would have been some 1,000 times higher. So I mentioned these drawings made by Russell Porter. He made these drawings between about 1937 and 1940, whilst the telescope was still being constructed. So in other words, he wasn't looking at the final thing and then making technical drawings. He was making drawings and imagining what the final result would be, and he could envisage the three-dimensional structure from the blueprints, and he could envisage what it would look like if it was sectioned in order to give a better idea of the three-dimensional structure of these various aspects. And that itself is pretty amazing. But the amount of detail, the sheer amount of detail that he's managed to put into these images is quite staggering, which is why I invite you to look at the PDFs that I'll make available to you in case you can't quite see the amount of detail that's here. This is the right ascension drive mechanism, and the original design included an analog computer so that the telescope wasn't simply driven at a constant rate, but the rate would be adjusted if there was any movement of the star because of, for instance, refraction of the light through the Earth's atmosphere, which changes as a function of altitude. That could be compensated by the analog computer, a series of gears and cams that was designed to vary the speed automatically. Quite an amazing idea. And I'm not going to spend too long on these because, as I say, I'll make these available separately, but that's a rather unusual view looking up at the horseshoe where you can't actually see the telescope itself. And this is pointing out the fact that the horseshoe itself is sitting on a number of these pads which have high pressure oil pumped into them, so that there's a very thin film of oil between the pads and the very heavy horseshoe and yoke and telescope to make sure that the whole thing moved essentially frictionlessly. A view looking down onto the south yoke, it reminds us that there is indeed room for an individual to walk up into the yoke arms themselves. And one of the reasons to do so is to walk into one of the yoke arms because that's where the declination motor and the declination controls sit. So if there's ever a need to do so, an engineer can walk inside the arms of the yoke to check out the declination drive. A view looking into the prime focus cage, we'll see more of that later. And this is what's going on inside the prime focus cage. Apparently, astronomers in those days used to wear a suit to do their observing. So here we have an individual looking through an eyepiece, perhaps checking that the star is in the right position, and photographic plates would be positioned at the prime focus to take wide-angle photography. Below the astronomer, the bottom half of the cage, that's where the pedestal is that the astronomer might sit at. But below that are the positions where the mirrors would fold into place to give us the Cassegrain focus or the Coude focus. And if it went to the Coude room, that's what the Coude room looks like. We'll see more of this in just a second. The light would come through the polar axis of the telescope and then bounce off one or more mirrors onto a diffraction grating and then produce a spectrum, which would then be caught with a photographic plate. So how are we doing with construction? Everybody thinks that everything is going wonderfully. The telescope looks just months from being finished. The telescope tube is finished, the telescope mount is finished, the mirror has been ground to within millionths of an inch of the correct final figure, so everything is looking hunky-dory. Except that it's now 1941 and America is about to join the Second World War, which means pretty much everything had to be put on hold. All of the mechanical workshops, all of the optical workshops had to be requisitioned for the war effort, and so the optical workshops were then put into use, I think, making tank periscopes and things like that, other optical components. So essentially nothing happened until 1945, and then you can bring everything back out of mothballs again. So in 1945, they uncovered the mirror. You can perhaps now see there's a little bit of a dish to the mirror because it's now been ground, and about 10 centimeters or more has now been ground away from the surface of the mirror, about 10 centimeters in the middle and rather less at the edges, of course. You also notice that the team of men is now complemented by a few women in the team as well. So they're starting to get the right idea. By 1947, they had done all the laboratory checks that they thought they could. Remember, the final check is put the mirror in the telescope and see if it focuses on a star. So as of 1947, they figured it was as good as their lab tests would allow them to actually tell. So in 1947, they took the mirror up the road to the observatory. And in 1948, they had the dedication ceremony. So at this point, the 200-inch telescope was dedicated to the memory of George Ellery Hale, who unfortunately had died a few years earlier. So Hale actually never got to see the Hale telescope. He got to see the plans for the 200-inch coming together, but he never saw it through to completion, which is a little bit of a shame. But again, an indication of the size of the whole thing. We're looking at here the bottom of the telescope and the observatory floor. At the dedication ceremony, I think there was something like 1,000 individuals on the observatory floor for that ceremony. So at this point, the 200-inch telescope became the Hale telescope. So given that was 1948, you could argue that the Hale telescope is now 72 and changed, 72 years old. The mirror was then bolted onto the telescope, point it at a star and see if the star comes to a perfect focus. They tried to work out whether or not there were any particular parts of the mirror surface that were just a little bit too high. The basic shape was right, but are there just a few little bumps of tiny little mountains that are just a little bit higher than they ought to be? They tried to work out where these high spots were. They're marked by little pieces of tape that you can see on the mirror surface here. The mirror is taken out, put onto a flat surface, and then the head polisher, or whatever his title is, then does the final polishing. We're now talking about small amounts being removed from the surface of the mirror. So we're not using a machine. A machine is too crude to take out these parts. This is done by hand. And for the last millionth of an inch or so, the amount that's taken off is tiny. The polisher might simply take a tiny bit of watchmaker's rouge and then just very gently wipe a thumb over the surface of the glass. That would be enough to take maybe a millionth of an inch or two off the surface. When he thinks he's got all of those high spots sorted out, the mirror would be put back in the telescope, pointed at a star the next night, and then again, you would repeat the process. If there's any parts of the mirror that look slightly high compared to all the others, out it comes, hand polish again, back in, check on a star, bring it out, back and forth until they were convinced that the mirror was as perfect as humanly possible. So in 1949, it was declared, that's it. Up to this point, there was no need to put a silver surface on it. It was perfectly adequate simply to look at the reflection from the glass. That would only be a percentage of the reflection from a silvered surface, but that's all you need to do a test. Once it was declared as finished in 1949, it was then coated with an aluminium surface, and then the telescope was operational. So it's been operational for approximately 71 years. Here's a view a couple of publicity photographs, one on the left of an astronomer sitting in the prime focus cage. Again, a reminder on the right, this drawing from Russell Porter, reminding you of what we're looking at. We're now looking from the top, effectively, into the prime focus cage. Here at the front, we have the escalator that brings the astronomer up to the right height so that he can then open this door and climb into the prime focus cage. As well as a photograph of that individual on the left, Hubble himself, Edwin Hubble, was photographed in the prime focus cage. Edwin Hubble, of course, had done a lot of pioneering work on the 100-inch Hooker telescope and was very much looking forward to using the 200-inch because that would allow him to take what was then the Hubble law and extend it into much more distant and fainter galaxies, hopefully confirming the law that he had established from data from the 100-inch Hooker. You appreciate that the astronomers there are open to the elements, and remember how cold it gets in the winter. So I'm sure all the astronomers in the prime focus cage were very grateful for the war surplus of electrically heated flying suits that became available. And I'm sure that they were there in their flying suits and with their sandwiches and coffee, trying to keep themselves warm for the duration of whatever number of hours they were observing for. This gives us an idea of what an observing session might have been like. No longer a suit, we seem to be in lumberjack mode now. So here the astronomer is going to take a photographic plate holder and place it in the middle of the pedestal in the prime focus cage. That will be locked into place, and then photographic film will be placed in that. No, that's not the film, put that back. Okay, the light tight box would be opened, and then that's better. The photographic film would be taken out and placed in the plate holder. This will be done in the dark, of course. And then the photographic back, that's it, he's got the idea now. Now the photographic back goes into position and holds the plate snugly in position. The astronomer would then decide to pick up a guide star. He would use the little eyepiece on the left-hand side to find a suitable guide star somewhere in the field of view just off to one side of the plate, find a guide star and put it in a couple of crosshairs, and that would allow him to double check that the telescope is pointing correctly at the star for the duration of the photographic exposure. He would then check that he's got his sandwiches and his coffee and everything else sorted out, and then he would actually expose the photographic plate, and that would start the exposure. And then for the remaining minutes or hours of the exposure, the astronomer would then check the guide scope and make sure that the telescope was tracking accurately and the guide star was staying centered in the crosshairs. If there was any tiny movement that he needed to correct, he could make very small corrections to the right ascension and declination positioning using a little paddle that was available in the prime focus cage. If instead the astronomer was working in the Coude room, again, remember from this drawing, the light comes down the central axis of the polar axis of the telescope and then enters this so-called Coude room. We can see a video on the left-hand side. It's reversed simply because the video is taken from the opposite side, and so it looks like the telescope is now on the left. So now the astronomer is checking that the light is coming down the polar axis of the telescope, and he's looking at the right object. He would then move that out of the way so that the light now falls into the right-hand side, and he would check that the light is entering the slits of the Coude room correctly to take a spectrum. And here's the Coude room itself. The light would be coming in the top right, hitting mirrors and the diffraction grating that we can see in the top right. And then the light would come down to where the astronomer is now placing a photographic strip, which would record the spectrum produced by the diffraction grating, separating the colors of the star or nebula or galaxy that's being studied. So we've looked at an astronomer in the prime focus cage and one in the Coude room. So there's the prime focus cage astronomer, and there's the astronomer in the Coude room. There's one other person in this particular drawing. I'm not sure if you can find where they are. Maybe you figured it out. They are there in the bottom right. There is the night assistant who helps the astronomer make all of these observations. There's a control desk there. And the night assistant and the astronomer have agreed on what objects they're going to be looking at for their observing session. And the night assistant would look at these dials here. These 6 dials are the hours, minutes, and seconds of right ascension and the degrees, minutes, and seconds of arc in declination. And one set of these 6 dials tells him where the telescope is pointing, and the other set of 6 dials tells him where the astronomer wants to point. And a very clever control system made up of self-synchronized motors, a very clever control system basically would move the telescope until one set of readings matched the other set of readings. Where you want to be and where you are would be matched together. And that in itself is quite a wonderful piece of engineering, which I haven't got time to go through in detail. But again, if you want to read the history of the 200-inch telescope, it's all laid out there for you. So 1 or 2 years after the first light in 1949, this image was taken, which brings me full circle to where I first started, because that is the image which first made me say, wow, this astronomy is pretty amazing. That was 1951. The following year, they took an image of possibly my second favorite object, the Helix Nebula. And this is a huge nebula. I'm not sure if anybody has tried photographing it. I photographed it with a 300mm lens, which tells you how big it is. It's about half the size of the full moon in the sky. So it's a huge wide angle. And I wondered, how on earth can you get such a wide angle using the 200-inch telescope? And I looked at this and thought, well, that's a wonderful image. Everything is beautifully sharp. But then I looked at what's going on with stars further towards the edge of the field of view. And you notice that those stars, let me blow them up a little bit, are very distinctly non-stellar. There is quite definitely chromatic aberration or coma in this particular optical system. This is something I talk about in a different talk, which I call Fiat Lux 2, in which I describe the fact that parabolic mirrors, and the Hale telescope was effectively the large, really big telescope to use a parabolic mirror. Parabolic mirrors suffer from coma or chromatic aberration. And coma means that when you go towards the corners of an image, the stars look more and more like little comets rather than pinpoints. Now, if you wanted to cure that, you could put a coma corrector before the photographic plate, but the bottom line was the Hale telescope was never really designed to be a telescope to take wide-angle pretty pictures. It was designed to look in detail at what's going on with either perhaps the central star or the nebula or the galaxy, usually in a much smaller field of view. Remember, we're often working with Cassegrain focus or Coude focus, much longer focal lengths. We're not working to such wide angles. But it's interesting to note that chromatic aberration was indeed present in this parabolic mirror system. The telescope itself, although it's 70 years old, has still found recent usage. We're talking 2013 here in this particular example. Because the Cassegrain focus, remember, you can put a lot of instrumentation behind that main mirror, up to a ton perhaps. If you've got a prototype instrument and you want to test it out, you need ideally to have a telescope with a big mirror, and you need to have a telescope which is capable of dealing with perhaps quite a heavy piece of instrumentation. So the Hale telescope is ideal for actually benchmarking and testing new ideas. And here they put a set of adaptive optics on the back of the Hale to see just how high a resolution could they achieve, as it were, retrospectively, with a monolithic mirror, but with adaptive optics at the Cassegrain focus. And here we can see the results from the Hale telescope compared to the Hubble Space Telescope. And you probably are thinking it's the other way around. The Hale telescope is on the left. The Hubble Space Telescope is on the right. So it shows you that if you have a good enough 5-meter mirror, and if your adaptive optics is clever enough, you can actually produce some absolutely fantastic images which are rivaling those of the Hubble Space Telescope. So that's a reminder that even though the telescope is 70 years old, if you look after it and if you have the right instrumentation, it can still produce some wonderful results. And if you are going to maintain it, it is 70 years old. That means occasionally you've not only got to give it a new lick of paint, every once in a while you're going to have to take the mirror out. So here is the mirror coming out, and it's being given a damn good clean. If you don't like the idea of thrashing your optics, look away now, because it starts to get very violent after a while. They don't just spray it with water, they give it a damn good cleaning. And then they put acid on the surface to actually remove the aluminium coating. So now we're down to bare glass. And then they give it another clean as well. So it looks quite rough, but of course they're trying wherever possible not to remove any of the actual glass surface so as not to ruin the figure of the mirror. By the time they finished, they've got effectively a pristine mirror, which is back close to the state it was in 70 years earlier when it was first declared in 1949 as a perfect mirror. Once they've got it clean, they just need to recoat it again in the evaporator, which is in the observatory, put another film of aluminium down on the surface, put it back in the telescope, and they're ready to go. So that's what the Hale telescope looks like today. If they continue to maintain it, if they continue to clean the mirror every year or two, if they give it a new lick of paint every now and again, there is no reason why the Hale telescope, especially if they put new instrumentation on it, there is no reason why the Hale telescope doesn't produce good science for years and years and years to come. You can use it as a test bed for new instrumentation. As long as it's maintained, it will be a perfectly good 5-meter telescope for years, if not decades, into the future. If you ever get a chance to visit Palomar in California, just southeast of Los Angeles, I suggest you do. When I visited it in 1982, I found it a wonderful experience, partly just for seeing such a wonderful instrument, but partly for the historical relevance of what it was I was looking at. So I've been telling you about George Ellery Hale, the billionaire whisperer who managed to get funding for 40, then 60, then 100, and then finally the 200-inch telescope. I talked about how a site was selected, how the mirror was made, how the telescope was made, and where we are now. I'll finish with some acknowledgements. The Caltech archives, the California Institute of Technology, has archives which give you a huge amount of information about Palomar Mountain. And the public affairs coordinator at Palomar produced a blog which gave me a lot of very interesting information about what it's doing now, as well as what it was doing in the past. And I'm grateful to the Corning Museum of Glass, who have archives from where I found the various pieces of video showing you how they poured the mirror. I took inspiration from a number of sources, including this book, Glass Giant of Palomar, in 1939. It was written just as the telescope was being made, so it wasn't made after it started operating, but was made just before the war started, showing you what state it was in. It's a wonderful read, giving you the entire history. Some of Russell Porter's drawings are in the publication on the right from 1952, republished in 1983 in the bottom left there. And there's also a more contemporary book, The Perfect Machine by Ronald Florence from 1995. The Perfect Machine is not bragging that it's a perfect machine. It gives you the mindset of the people who tried to design and build it. They tried not to compromise because they wanted to produce a perfect machine. So the Hale telescope has been at the cutting edge of astronomy research for about half a century. There are very few scientific instruments that can make that claim. It was the biggest telescope in the world when I was born. It was the biggest telescope in the world when I went through my childhood. It was the biggest telescope in the world for a lot of my adult life. And the fact that it is still producing good work is testament to the scientists who designed it, to the engineers who built it, and testament, most of all, to the vision of the one person who made it all come together, George Ellery Hale. Thank you all very much for listening.